Welcome, quadrature fans. My name is Professor Theoremus Antiquitus, also known as Mary and Elena. Okay, so today we'll come back to y equals x squared, but we'll come back from a setup that aligns more with Professor Norman Wildberger. And I am referencing, I got notes this time because I make a lot of mistakes, but Norman Wildberger, he had an article in the American Monthly, Mathematical Monthly, November 2002. The title is A New Proof of Cavalieri's Quadrature Formula. And there it's basically set up, and that's kind of the setup we're going to go. As you may know, for review, my setup before in the previous videos, and you might want to review those. Well, we would go something like this. If I have y equals x squared, I have 4 partitions, 0a, 2a, 0a squared, 4a squared. Because 2a times 2a is 4a squared. That's why you need 1, 2, 3, 4. If I had y equals x squared, I would have 8 partitions, because 2a times 2a times 2a would be 8a third. We're dealing with squared. We'll go to x third. Eventually we will prove xn. Okay, so with a Wildberger setup, we go from 0 to 1, and then go 1 plus c. That's on our x-axis, meaning that this distance is 1, and this distance is c. And we can also draw it using the t-axis, 0c minus 1. You see how this is 0, this is c. And of course I need to draw my curve. Y equals x squared. And so it's going to be something similar, but a little different, okay? And you'll see it. You'll see the differences. So translation under Wildberger's setup. And remember, we are using his 5 properties of areas: linearity, additivity, translation, dilation, normalization. 5 amigos. Okay. So x is equal to 1 plus t. You see this? This is the setup that we're using. When t equals 0, x is equal to 1. When t equals c, x is equal to 1 plus c. When t equals minus 1, x is equal to 0. So it all adds up. Okay, so y equals x squared. That means y equals 1 plus t squared. Okay, crank that through. So y equals 1 plus 2t plus t squared. Something similar along the lines that I did previous, but you'll see the differences. And we're going to show these 3 functions. This function from 0 to c. When you plug in when you plug in t equals c, you get c squared. When you plug in t equals 0, you get 0, right? So that's that. So that's that one. That's our quadratic term. Now we also have this linear term, and you plug in t equals c. So what does that look like? Well, that looks like a linear term. 0 to c. And this is 2c. Alright? A little bit different. This one's c squared, this one's 2c. Okay. What about this one? Well, that's just the constant. And that one is just, from 0 to c, that's just 1. So here you have it. You have these three functions. You have 1, you have 2t, and that's always on the interval from 0 to c. And this one's, you plug in c, you get c squared. And you squish these together, you slice this up using Cavalieri's shifting principle. This area here becomes that. This is c squared, this is 2c, this is 1. And so it is a little bit different from what you've seen before. In my setup previously, we see a squared, 2a squared, a squared. Here we see 1, 2c, c squared. So we have kind of an incrementing c, power of c. C to the 0, c to the 1, c to the 2. And with this, we'll do the area. And that's kind of what Professor Wahlberger does, except he does it not for y equals x squared, he does it for y equals x to the n. And we're going to work up to that. We're not ready for that, not yet. Professor Wahlberger says that that's high school stuff. Maybe, but it's tough stuff. I like to see pictures, and it needs to be digested. So we're going to digest Wahlberger, okay? One term at a time. We're going to work up to it. So x squared, then x third, maybe x fourth, and then I'll bring it up to x to the n. Slowly. We got plenty of time. So, slope. Well, how would we set up our slope? It's basically this big slope right here is equal to a combination of little slopes. Sorry, scratch that. Not slope. Area. We're going to do the area first. One thing I want to mention that Professor Wahlberger, he only did the area. He didn't do the slope, the tangent slope, and that's kind of a difference between my approach and his approach. In that Mathematical Monthly, November 2002 issue, it only does the area. In my approach, I do area and tangent slope, and I do them almost simultaneously with one setup. And so that's kind of unique. And so it's going to pick up on Wahlberger. And all right, so the area. We're talking about this big wedge. What is that? Well, oh, I forgot something here. This is 1 plus c squared. The base is 1 plus c. The height is 1 plus c squared. So the area would be K2. That's our ratiometric isoinvariant times base times height, or height times base, whatever you prefer. It really is 1 plus c k2 squared times 1 plus c, right? Which is really 1 plus c to the third power. Well, that equals these, is it 1, 2, 3, 4 individual areas. This one here, K2 times, again, 0, 1. This is just K2 times 1 plus this one. What's that? Well, that's just C times 1. Nothing to it, right? Plus C. C times 1, 1 times C. Right? Plus the linear term. Linear term is 1/2, that's our K factor for linear, times C times 2C. Right? Base times height. Base times height. That comes right out of here. Plus the quadratic. Well, again, that's going to be our unknown K2, which we already know it's 1/3, but we'll prove it's 1/3 again. K2, not K3. K2 times just base times height, right? C times C squared. And it's, okay. We're going to have to crank this through, which we already know as K2 1 plus C to the third. And we always are using Pascal's triangle for these things because that helps us, right? We're on this line here. It's the third. That equals this whole thing, right? So K2, it's going to be 1 plus, well, it's 1 to the third, which is 1, plus 1 squared times C, so it's really 1 times C plus 1 times C squared, right? C squared. Plus, oh, wait. But I'm forgetting. I need my 3. 3 times this. Okay. Plus 3 times 1 times C squared. Plus 1 times C to the third. Okay. Whew. Let's pretty this up. It's kind of hard to see. So we got K2 1 plus 3C plus 3C squared plus C to the third equals K2 plus C squared plus K2 C to the third. Okay, look at this thing. This is an equation, and there are going to be things that always, they cancel out, and the other things there are left. Namely, K2 times 1, that cancels K2. Alright? You guys see it?
Yes.
Yeah. So this and this cancels out. Alright. K2 times C third, well, that's this term. That's out. So we really only have, look at this. This is it. And all right, let's rewrite it. K2 times 3c. Well, I'm gonna factor the 3 out of it right now. I can do that, right? Pull the 3 out, times 3 times c plus c squared equals c plus c squared. You see this? See what happens? Therefore, K2 equals 1/3. Pretty easy, isn't it? Yeah. That's one way to do it. The other way to do it is just collect your C's, you know. The C's must match with the C's. The C squareds must match with the C squareds. You can get the same thing out of it. So what does that say? It says K2 times 3C. K2 times 3C is equal to 1C. Well, the C cancels out. From this we get K2 equals 1/3. See it? That's from these two. But what about this? Now you collect your C squareds. It's redundant information, but you get K2 times 3C squared equals C squared. And that gives you K2 equals 1/3. Again, this is redundant, but at least it agrees. It didn't say K2 is 1/4. They better agree. You know, you look at the C's must match with the C's. And they balance out. And they give you the right number. K2 is 1/3. K2. All right. So that's that one. Okay. That's the area. But here's something that Professor Weilberger didn't do, and that's slope. So we figured out that K2 equals 1/3. Now we want to find out what the slope factor is, and we've been using, you know, numbers like K2 and C2. Don't get that confused with a C over here, or C squared. This C2 is, I could have used D2 or L2 or something else, but in my previous video I try to standardize. The C would represent the ratiometric invariant for the slope, tangent slope. So I want to be consistent with that. So we're gonna do that. So let's set it up. And to set that up, well, we're going to ask ourselves on this big wedge, what is the slope? And the slope is C2 times the rise divided by the run, the characteristic diagonal. See that? That's what we're after. Okay? That's 1 plus C squared divided by 1 plus C. Rise over run times C2. And don't forget, C2 here doesn't have nothing to do with C over here. They're totally separate variables. Equals the individual components of these functions. The component of this one, which is 0, that's the constant term, plus the linear term. Well, that's 2c over c, right? Rise over 1 plus 2c over c plus, and then look at this, And by the way, that's 1 times, and this is plus 2 times, no, plus C2 times. This is unknown, I forgot. C2 is our unknown so far. We know it from previous, it's 2, but not yet. The rise over the run times C2, so it's C squared divided by C. Let's simplify this. We get C2, 1 plus C equals 2 plus C2C. Okay? All right. Well, let's crank this through. C2 times 1 plus C2 times C. And again, this C and this C2 are completely different variables. Equals 2 plus C2 times C. Well, this cancels out. And voila, we get C2 is equal to C. C2 is equal to 2. That's what we're after. And we got it using a little bit different setup, the Wahlberger setup. So there you go. Y equals x squared. We're doing the areas and also the slopes, something that Professor Wahlberger didn't do. And but I had some time to think about it. I had plenty of time. And again, our approach is unique. We're looking at slopes and we're looking at areas and we're looking at them almost simultaneously with basically one setup, one equation, and we're getting it, you know. So that's what we're after. So okay, I think we're going to call it quits. Hold on. So remember, before there was calculus, there was
quadrature.